Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at d-orbital splitting. We're going to talk about what d-orbital splitting or crystal field theory actually is, why it can occur in transition metal ion complexes, and the factors that can affect the level of splitting. Transition metal complexes and their properties, including color, have been covered in separate videos. Check the links in the description below. Before we talk in detail about d-orbital splitting, there are a few essential ideas you need to be comfortable with. Transition metals are metals that can form one or more stable ions with a partially filled d subshell. In other words, ions of these metals always have at least one half-filled d orbital. Inside an atom, electrons exist in regions of space called orbitals that make up subshells in given energy levels. One orbital can hold a maximum of 2 electrons, each with opposite spin. Different orbitals have different energies depending on their shapes and distances from the nucleus of an atom. D subshells contain 5 orbitals that have different shapes, called d-orbitals. Only the third energy level and above in an atom can contain a d subshell. A d subshell can hold a maximum of 10 electrons, 2 per d orbital. Recap done? Let's go! A gaseous free transition metal ion has electrons in its outer d subshell. All the orbitals within the d subshell are at the same energy, meaning it doesn't matter which orbital electrons fill first. As they all have the same energy, we describe them as degenerate. For example, a gaseous titanium 2+ ion has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. This means there are 2 electrons in the outer 3d subshell of the ion. As all the 3d orbitals have equal energies and are degenerate, it doesn't matter which orbitals the electrons go into, as long as they half fill 2 rather than completely fill 1 due to spin pair repulsion. If a transition metal ion forms coordinate bonds with other atoms or ions, however, the energies of specific outer d orbitals can change, leading to electrons in different d orbitals ending up with different energies. For example, if a transition metal ion is dissolved in water, water molecules surround the ion and 6 water molecules act as ligands and form coordinate bonds to it. This forms a metal aqua complex ion with an octahedral shape. If you're unsure about this, please check the video on complex ions, link in the description below. Now, the interesting thing here is that as the water molecules, or ligands, approach the ion, the electron pairs forming the coordinate bonds can interact with electrons in the outer d orbitals of the ion. For an octahedral complex with 6 ligands, 2 outer d orbitals experience more repulsion with the electrons from the incoming ligands. This is due to the shape and arrangement of the d orbitals. Any electrons in these 2 orbitals would be close to the incoming electron pairs from the ligands, leading to repulsion. As a result, their energy would increase and they would now be at a higher energy than the electrons in the other 3d orbitals. This means then that as an octahedral complex forms and 6 ligands bond to a transition metal ion, the d orbitals in the ion's outer shell split in energy. 2 of them, dx² minus y² and dz² to be specific, increase in energy more than the other 3, dxy, dyz and dxz. There is an energy gap between the split d orbitals. The electrons in an ion's outer d subshell are always going to occupy the lowest energy orbitals available, meaning the dxy, dyz and dxz orbitals fill completely with electron pairs before the dx² minus y² and dz² orbitals fill. As transition metal ions always have at least one half-filled or empty orbital in their outer d subshell, one of the higher energy d orbitals will always have at least one available space for an electron. If an electron in an orbital in the lower energy set is given the exact energy matching the energy gap between the split d orbitals, it can be excited to one of the available spaces in the higher energy set. When this happens, the electron is said to have been excited from its ground state, lowest energy possible, to an excited state. Usually, the energy required to do this can be found from waves of visible light from the visible region of the electromagnetic spectrum, and this is why transition metal ions form coloured compounds. Again, this ability of transition metals to form coloured compounds has been covered in more detail in a separate video. Check the links in the description below. We can actually calculate the energy gap between the ground state and excited state if we know the frequency or wavelength of light absorbed by an electron as it gets excited. Delta E, the energy gap, equals Planck's constant h multiplied by the frequency of the wave absorbed. As the frequency of a wave equals wave speed divided by wavelength, or lambda, this means the energy gap or difference equals Planck's constant h multiplied by wave speed divided by wavelength, lambda. As the waves are light waves, the wave speed will always be c, the speed of light, approximately 3 × 10⁸ meters per second. The energy gap between the split d orbitals in a transition metal ion complex is determined by two things: the mass-to-charge ratio of the metal ion and the ligands bonded to the ion that caused the splitting in the first place. Different metal ions have different mass-to-charge ratios, and this means the energy gap is different for each. This is why different ions form different coloured solutions and precipitates, as electrons in the ground state of their outer d orbitals absorb slightly different wavelengths of light to become excited. Ligands can also have a small effect, which is why colours of complexes can sometimes change during ligand substitution reactions. For example, iron ions with an +2 oxidation state, iron 2, form green solutions when dissolved in water, whereas iron ions with a +3 oxidation state, iron 3, form red-brown solutions when dissolved in water. This is because the mass-to-charge ratio for the Fe2+ and Fe3+ ions are different, meaning that outer d orbitals are split by different amounts of energy given a different energy gap, and meaning different wavelengths of light are absorbed as electrons get excited from the ground state to an excited state. So, to summarise, the outer d orbitals of a gaseous transition metal ion are all equal in energy. They are considered degenerate. It doesn't matter which orbitals electrons occupy first, they all have the same energies. If atoms or groups form coordinate bonds to a transition metal ion, however, the electrons forming the bonds interact with the electrons in the outer d orbitals of the ion. For an octahedral complex with 6 groups bonding to a transition metal ion, electrons in 2 of the outer d orbitals experience more repulsion with the electrons from the incoming groups, and their energy increases. This means the 5 outer d orbitals of the transition metal ion get split into 2 sets, higher energy and lower energy. An energy gap exists between the 2 sets, and electrons can be excited from a lower energy, ground state d orbital to an available space in a higher energy d orbital, an excited state. To do this, they have to absorb the exact right amount of energy. The energy needed can often be found from waves of visible light from the visible region of the electromagnetic spectrum, and this is why transition metal ions form coloured solutions and precipitates. The energy gap delta E between the ground state and excited state equals Planck's constant multiplied by wave frequency. As the frequency of a wave equals wave speed divided by wavelength, this means energy gap equals Planck's constant multiplied by wave speed divided by wavelength. The wave speed will always be the speed of light, c, as the wave is a light wave. The energy gap between split d orbitals is determined by the mass-to-charge ratio of the metal ion and ligands attached to it. This is why different transition metal ions and their compounds can have different colours, depending on the oxidation state of the metal and the groups bonded to it. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.